Here's my solution for the list of image data definition. It's an ordinary self-referential data definition of the kind we saw previously. There's two cases, the base case and the self-reference case. And I've got an example of the empty list, as well as an example of a list that has a couple images in it. There's the template. This week you're allowed to not start including template rules used. That means you don't have to write the template rules used. So I'm not going to write the template rules used. But as you read it, I think you can go through the template rules used in your mind fairly quickly. It's a one of with two cases, so there's a two-case con. The first case is atomic distinct empty. We have the usual empty LOI ... And then there's a cons of a primitive type image. So we just have first LOI, there's no call to a natural helper, and the natural recursion. So there we go, there's that data definition. Now let's get on to designing the functions. We'll make another part of the file called functions. And we're supposed to design a function called arrangeImages that consumes an arbitrary number of images. So that means it consumes list of image. And it produces an image in which they're all laid out left to right. So that's going to produce a single image where all the images are laid out left to right in increasing order of size. So what does it have to do? It has to lay out images left to right in increasing order of size. Okay, so a good stub for this function is just define arrangeImages, LOI, and a good stub is blank. By this point, we've seen that these functions that produce images often use blank both in their stub and in their base case. So I'm going to go ahead and make a constant for it. Square, 0, solid, white. Now I've got a constant I can use here in this stub. I'll run everything. My stub is well formed. Let's do some check expect. Let's see, check expect, arrange images, empty. Well, if I ask you to arrange an empty list of images, then that's just going to produce blank. And let's see, we want to do one for a non-empty list. It should be at least too long. Let's see, we need to arrange images. And what I'm going to do is I'm going to use the same list that I defined up above, but I'm not going to refer to it as a constant. And I'll tell you why I'm going to do that, which is it's going to make it easier for me to understand my check expect as an example if I actually include the full calls to rectangle here, because I really understand what I'm seeing. So now let's see, if I need to arrange those images left to right in increasing order of size, well, the area of this image is 200 and the area of this image is 600, so they already are at increasing order of size. So I think this is going to be beside of this rectangle, then this rectangle, and also blank. Now you might ask, why are you putting the blank there? If the blank is blank, in other words, it's nothing that you see, then it doesn't really make sense to put it there because it's blank. Well, that's true, but the reason I'm putting the blank there is, remember, check expects are examples before they're tests. And by putting the blank there, I'm kind of reminding myself, you know, what gets built up is the blank from the empty and then the other two images. That's why I'm putting the blank there, is to make it clear to myself not just what the actual final image is, but in some sense why it's the image that it is. We'll run it. They fail, but they're well formed. That's great. Now, I'm going to get the template. I'm going to put the template in. I'll rename it. I'll rename the natural recursion. I'll comment out the stub. And now I'm going to think for a minute. And what I'm going to do is I'm going to go back and reread the purpose. And the purpose says lay out images left to right in increasing order of size. And what does that mean? Well, if I think about it for a minute, what it means is sort images in increasing order of size and then lay them out left to right. Really what I have to do to make this problem work is first I have to take the entire list of images and I have to sort that entire list. And then I have to lay those out left to right with beside. I can't really go through the images one at a time and sort each image and lay each image out. The sorting has to be done to the whole list, and then the laying out has to be done to the whole list. This is what's called a function composition problem. And if we go to the design recipes page, there's a special entry for function composition. And it says that you use function composition when a function must perform two or more distinct and complete operations on the consumed data. For example, and it has this example, that's convenient, a function that must sort and lay out a list of images. I won't read through the page now. You should do that afterwards very carefully. But what happens in function composition is that we discard the entire template and we replace it with a function composition, such as this one. And it's called a function composition because what it says is it says first sort the entire list, first call sort images to sort the entire list, then take the result of that and call layout images on it to lay out the entire list. So the functions happen one after another, each on the output of the previous function. So this is a two-function composition. You could also have problems that had 3 or 4 or 5 functions. They tend to be weighted more towards the smaller number. This is a two-function composition. Now, of course, I've wished for some functions that don't exist yet, so I better do wish list entries. Let's see. Layout images consumes list of image and produces image. Place images beside each other in order of list. It's a wish list entry, so we'll do that. And it's got to produce some image. So that's the wish list entry for layout images. Let's look at sort images. Well, sort images consumes a list of image, and it produces a list of image. Sort images in increasing order of size. It's a wish list entry. Now this is a function that produces a list. So we could put just empty as the stub here. What I'm going to do instead of putting empty is I'm going to put LOI. Because I know that when the stub is called, LOI will be list of image. And so if I produce LOI, I know I'll be producing list of image. And you'll see a little bit later that this slightly different stub, this slightly more clever stub, actually helps us in seeing how the program is coming together. So I'm putting that as my stub. Now that I've set up these wish lists, and I know that this is a function composition function, there's one more thing I have to do, which is I have to go back and think about these tests one more time. And here's why. If a function is a function composition function, then the tests for it have to make sure that it's composing the functions properly. They don't have to exhaustively test the individual functions. The tests for layout images will test layout images, and the tests for sort images will test sort images. The tests for arrange images have to make sure that arrange images is calling layout images and sort images properly. One thing this means is that when you go to a function composition, you don't need to test the base case. But another thing it means is that because this function is supposed to both sort and arrange, this test isn't good enough. because a version of this function that just did the rendering would work, because these are already in the right order. So I need a second test. I need at least one more test in which I make sure I'll just swap these two rectangles around. And I won't swap them down here, because the point is that what arrange images needs to do is call sort images to rearrange these in the right order and then present them. So now I feel like I've really tested that arrange images is doing both jobs, both the sorting and the laying out. At this point, you're basically done with arrange images. If you ran it, the test would run but fail. The reason they would run is because we have the wish list entries. But they would fail because the wish list entries aren't doing the proper thing for either of these functions. So to recap this video, remember the first part of the week is about more rules for helper functions, more rules for when to split one function into multiple other functions. And in this video, what we saw is the function composition rule, which says that we should use a function composition when a single function must perform two or more complete operations on the entire consumed data. So in this case, for example, we have to sort the list of images and then lay out the list of images. That's a function composition problem. So what I'm going to do with this picture here is I'm going to keep updating it through the next several videos to show how we've broken the original problem of doing arrange images down into multiple functions and which rule we used at each point. When you start to get into bigger programs, lots of programmers keep an actual pad of paper by their desk to kind of keep track of where they are in something. The wish list entries are good for that, but some notes and pieces of paper like this are good for it too. There's also professional programming environments like Eclipse that can help you in some ways draw pictures like this to keep track of where you are as well. That's something you could learn about in another course.